Today we're going to discuss some issues about risk and return as they relate to investing, and this is going to lead into Chapter 11 where we're going to talk about the capital asset pricing model. So what we're leading up to now is how do we come up with the discount rate that we use to calculate net present value. The key concepts, how to calculate the return on an investment, standard deviation, historical returns and risks of various types of investments. We'll talk a little bit about the normal distribution and understand the difference between several different kinds of averages, arithmetic average and geometric average. Chapter is outlined as you see. So here's a typical investment. Initially at time zero we put some money in, and then 1 year later we get some money out. If it's a stock, the money we get out is in the form of dividends plus the market value of the stock at the end of the period. The return would be the sum of the cash received and the change in the value of the asset divided by the initial investment. So there you go. The dollar return is equal to the dividend plus the change in market value. The percentage return is equal to the dollar return divided by the beginning market value. If we substitute in, we see that the percentage return is equal to the dividend plus the change in market value divided by the beginning market value. And that works out algebraically to equal the dividend yield plus the capital gain yield. Some of you may recall when we talked about bonds, we had the current yield plus the capital gain. Now we're talking about stocks. We have a dividend yield plus a capital gain. Here's an example. Suppose you bought 100 shares of Walmart stock a year ago for $25. Now the stock is worth $30, and in the meantime the stock has paid 20 cents a share, or $20 for 100 shares. How well did you do? What was your return? Well, you put in $2,500. Your investment is now worth $3,000, and you got a cash dividend of $20. So your dollar gain would be, well, $500. That would be the capital gain plus $20, or $520. If we divide that by the initial investment of $2,500, you see that you got a return of 20.8%. So there kind of is putting some numbers into the graph we had previously. Okay, now holding period return is a return you would get over an investment if you hold it for a number of years, say n years, where the return each year is given by R sub I. And the holding period return is equal to the product of 1 plus the individual annual returns, the return for year 1, the return for year 2, up to the return for year n, and then we subtract off the 1. Here's an example. Suppose in year 1 we earn 10%, year 2 we lose 5%, year 3 we gain 20, and year 4 we gain 15. If we multiply 1 plus each of those returns, so 1 plus 10% is 1.1, 1 plus a negative 5 is 0.95, 1 plus 20 is 1.2, and 1 plus 15, 1.15. Multiply those together and subtract 1. We get a holding period return of 0.4421, or 44.21%. A couple of guys, Ibbotson and Sinquefield, up in the University of Chicago, did a study where they looked at the rates of return of stocks, bonds, and treasury bills and other securities. They started in 1926, and they looked at 5 important types of securities. They looked at large company stocks, small company common stock, corporate bonds, U.S. government bonds, and they looked at U.S. treasury bills. They looked at a couple of statistics. The first is the average return, where they took the return for each year, added them together, and divided by the number of years. And the standard deviation, which is, we're going to have more to say about, but is that kind of ugly-looking formula there. And this is what they discovered between 1926 and 2004. Large company stocks, for example, had an average return of 12.4% and a standard deviation of 20.3%. If you look at a histogram showing the distribution of returns by percent, it looks something like this. So it's a little jagged, a little hard perhaps to make out any smoothness to it, but as you can see, the amount that it's spread out from left to right is sort of what the standard deviation measures. Now if you look at small company stocks, the average return over that same period was a little higher, and the returns are more spread out, so the standard deviation is even higher. And in fact, in general, if you look at this closely, you'll see that there's kind of a positive correlation. As the return gets higher, so does the standard deviation of returns. Okay, so we talk about a risk premium. What is a risk premium? Well, if we could think of something as representing a risk-free rate, the return on a risk-free rate, the risk premium would be the amount we earn in excess of the risk-free rate. You could think of it as the extra return that you receive from because you're taking risk. One of the most significant observations is that this excess return is fairly stable. Observation is here that stock market data in the long run excess of stock return over the risk-free return is fairly stable. And for average long-term common stocks, large company common stocks, the risk return has averaged about 8.6%. That is the average return for large company common stocks, 12.4. The average risk-free rate about 3.8, and the average risk premium about 8.6. For small company stocks, risk premium 13.7, and for long-term corporate bonds, the risk premium over this period averaged around 2.4%. Now, risk premium are fairly stable, so suppose that the Wall Street Journal announced that currently the one-year Treasury bill, which we will use as a proxy for the risk-free rate, is 5%. Then we could estimate what the expected return on small company stocks would be. We'll assume that the risk premium is fairly constant at 13.7, and we'll add 5 plus 13.7 and get an expected return of about 18.7%. So that would be a good estimate of what we think the return on small company stocks will be, given that the risk-free rate is around 5% and given that the risk premium is fairly stable. The risk-return trade-off can easily be seen in a graph. On the horizontal axis, the x-axis if you will, we have standard deviation, and on the vertical axis we have annual average return, and those have been plotted for 4 different types of securities: Treasury bills, Treasury bonds, large company stocks, and small company stocks. And you see that positive upward slope suggesting that as risk increases, so does annual average return. Let's talk about some risk statistics. First of all, there is no universally agreed definition of risk, and we could talk about that for some time. I think for most people, risk means the probability of failure. But in finance, we're going to let risk represent the probability that we will miss the expected guess or the expectation. So we use standard deviation and variance quite often as a measure of risk. Standard deviation is a measure of the standard statistical spread of a sample, and we're going to look at the calculation of that. So here's a typical normal distribution. Now, let me be clear about why the normal distribution is important. The normal distribution shows up anytime we start looking at distributions of averages. So if I take any population whatsoever, and I take a sample, and I calculate the average of the sample, and then I take another sample, random sample, and I take the average of that sample, and I keep doing this for a number of samples, and I plot these averages, what you will see is that the averages of the sample means, the sample means, look like a normal distribution. So it's a very important distribution. Basically, what do we see here? We see in this particular example that the mean is 12.4%, and we see that 68.2% of the observations lie within 20.3%. Now 20.3% is one standard deviation. So two-thirds, approximately two-thirds, a little over two-thirds of the observations on a normal distribution lie between plus or minus one standard deviation from the mean. Now about 95% of the observations lie within 2 standard deviations from the mean, and about 99%, almost 100% of the observations lie within 3 standard deviations of the mean. In the literature, you'll hear people talk about a 2 sigma event, or a 3 sigma event, or a 4 sigma event. By a 3 sigma event, someone would mean an event that is 3 standard deviations away from the average and is quite unlikely to happen. The 20.3% standard deviation you may remember from the Ibbotson and Sinquefield data between 1926 and 2004 was for large company common stocks. That was the standard deviation, and the stock return was about 12.4%. And what we can see from the normal distribution is that about 2/3 of the observations, of the observed returns in that sample, should be between 12.4 minus 20.3 and 12.4 plus 20.3. So here we go. Here's an example of how to calculate return and variance and standard deviation. So here are 4 observations. We have a year 1, year 2, year 3, year 4. In year 1, the actual return is 15. In year 2, it's 9. In year 3, it's 6. And in year 4, it's 12. Now if you add those 4 numbers together and divide by 4, you'll get the arithmetic average, and that will turn out to be 10.5. So notice next to each return we've put the average return, and then we've subtracted the actual return. From the actual return we've subtracted the average return. So 0.15 minus 0.105 is 0.045. And 0.09 minus 0.105 is minus 0.015. 0.06 minus 0.105 is minus 0.045. And 0.12 minus 0.105 is 0.015. Now it will always be true that if you take the deviations from the mean, so here's the mean, these are the deviations from, and you add them up, they will always add up to 0. That's easy to prove. So that's not very useful to us. So what we do is we take the deviations and we square them. And when we square the deviations, they all become positive. And then we add up the deviations, and that's the squared deviation. And then we take the squared deviation and we divide by n minus 1. And the reason we divide by n minus 1 has something to do with statistics and degrees of freedom. We have 4 degrees of freedom because we have 4 observations. What that means is we could fit 4 different functions to this data, and we've already fit 1 because we've already computed the mean, so we only have 3 degrees of freedom left. So we divide by 3, and we get a variance of 0.0015. Now if we take the square root of variance, we get the standard deviation. The reason people calculate standard deviation is that standard deviation is in the same units as the original returns. So standard deviation here of 0.038 could be interpreted as 3.87%, whereas variance is in percent squared, and it's a little difficult to interpret what that means. Now we can talk about geometric means, and I've just shown you arithmetic means, and we can talk about the difference. An arithmetic mean, that's where we add up all the observations and divide by the number, is the return earned in an average period, say an average year, over multiple periods. A geometric average is an average compound return per period over multiple periods. And the geometric average will always be less than the arithmetic average unless all the returns are equal. So unless we have 10%, 10%, 10%, 10%, every year we have the same. Then the geometric and the arithmetic averages would be the same. Which is better? Well, depends on whether we're interested in a long-term or a short-term horizon. The arithmetic average is overly optimistic for long horizons, and the geometric average is overly pessimistic for short horizons. And so let's look at another example. Let's look at an example of the geometric return. You recall from the earlier example we had 10, minus 5, 20, and 15. And if I just do this in my head, plus 10 minus 5 is plus 5, and 20 is 25, and 15 is 40. And if we divide by 4, the average return was 10, the arithmetic average. Now let's do the geometric average. We take the annual return for each year, we add 1. So basically we're calculating 1 plus a holding period return. We then take the fourth root of that product, and then we subtract 1. And you see in this case we got a 9.58%. And as predicted, the geometric average is less than the arithmetic average. So what that says is that an investor made an average compound annual rate of return of 9.58%, giving them a holding period return of 44.21%. Note that the geometric average is not the same as the arithmetic average, and that's because all of the observations are not the same. So the arithmetic average was 10%. The geometric average was less than 10. It was 9 something. Now, which of these should we use? To address this question, we introduce Bloom's formula. And Bloom's formula says that the return for a period of time that we should use in forecasting is equal to t minus 1. Now, n is the number of years that we've got data for, and t is the point in time somewhere between 1 and n that we're interested in. So so we have t minus 1 divided by n minus 1 times the geometric average plus n minus t divided by n minus 1 times the arithmetic average. Now just to give you an idea of what this formula does, it's a weighted average of geometric and arithmetic. Suppose that t is 1. If t is 1, in other words, if we're interested in a return for just the first year, you see that on the left-hand side t minus 1 would be 1 minus 1, that's 0. And this would put a weight on the geometric average of 0, and n minus 1 divided by n minus 1 is 1, and so it'll put 100% of the weight on the arithmetic average if t is 1. Now if t is n, it does exactly the opposite. If t is n, then we get n minus 1 divided by n minus 1 on the left, so 100% of the geometric average, and n minus n is 0 on the right, so we have 0% on the arithmetic average. So again, what this does is if t is long, we choose the arithmetic average. If t is very short, we choose the if t is very short, we choose the arithmetic average. If t is very long, we choose the geometric average. All right, that pretty much completes our discussion of Chapter 10. Let's review. Which of the investments discussed had the highest average return and risk premium? Well, that would have been small cap common stocks of the Ibbotson and Sinquefield data that we looked at. Which of the investments discussed has had the highest standard deviation? Well, same answer. It would be the small cap common stocks. Why is the normal distribution informative? Well, the normal distribution shows up often, especially when we're looking at sampling data, and that's one of the reasons it's so very important, extremely important in hypothesis testing. What's the difference between arithmetic and geometric averages? Well, generally, the geometric average gives us a compound annual rate of return, and arithmetic average sort of tells us what the average return would be in just one given year. So we can think of it that way, and that pretty much finishes up our chapter.